This is Jack Jackson. In this video we're going to talk about the Fundamental Theorem of Calculus, and we're going to summarize what it says and give some basic interpretations of what it means. So this is a basic overview. In the previous videos we kind of discovered this basic result, very, very important, probably the fundamental result as the name suggests in calculus, and we also did a proof of it. So we're going to basically talk in this video about what do we discover and give a summary of that. So we could state the fundamental theorem of calculus like this. If f of t is a function that's continuous on a closed interval from a to x, then first of all, if we integrate f of t dt from a to x, a definite integral, that gives us a function of x. We turn around and take the derivative of that, integrate first, then take the derivative with respect to x, that gives us a function of x, which turns out to be the same as the original functions of t evaluated at x. So in some sense, the integral first, then the derivative cancels each other out. And number two is kind of backwards from that. If we take a function and take its derivative, here we're assuming the function f, I guess, is differentiable on this interval, take its derivative and then integrate that from a to x, then that turns out to be f of x minus f of a, or equivalently to the second part if we write it this way. If f is any antiderivative of a continuous function g, in other words, f prime of x equals g of x, at least on that interval from a to x, then the integral from a to b of g of x dx equals f of b minus f of a. So let's make sure we understand this. G is the derivative of the f. F is an antiderivative of g. Notice that I said the derivative and an antiderivative. The derivative process generates a single derivative. So if I have the function f, there will only be one derivative for that function g. But if I have a function g, there might be more than one. In fact, not might be. There are infinitely many different antiderivatives, all of which differ only by a constant. And no matter which one of those you do, you can pick any one of those antiderivatives, f, for g, evaluated at both endpoints and subtracts. So what are some things that what are some big ideas that we get out of this? Well, the first thing is that these are inverse operations then, differentiation and integration, at least in some sense that's defined by this fundamental theorem, are basically inverse operations, and they sort of cancel each other out. So taking a derivative and then an integral gives you back where you started. If you take an integral then a derivative, you're back where you started. So at first glance this might be a remarkable result, because let's think about what we had. So remember, our definition of a derivative is the limit of a difference quotient as delta x approaches 0. So that is, the derivative of f with respect to x, or f prime of x, is defined to be the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So it's a limit of a difference quotient. So geometrically, the derivative at a point is the slope of the tangent line to the curve at that point, and it's the instantaneous rate of change in the function at that point. So derivatives are slopes, rate of change. On the other hand, a definite integral, okay, is defined to be a limit of Riemann sums. So I did in this class we do a limit of right Riemann sums. So we first of all divide the interval up into subintervals, all of width delta x, which is b minus a over n, so that they're all equal width. We let xk be a plus k delta x, which puts xk at the right of the kth interval of x. We take the y value at that xk, that would be f of xk, gives us a height of a rectangle, or a signed height, and we multiply that by width, delta x, of that interval, and that gives us a rectangle. So we have a rectangle of width, delta x, and height, f of x sub k. That gives us the area of one rectangle. Then we add that up from k equals 1 to n, gives us a sum of the areas of the rectangle. So the product was an area of one rectangle, then that sum is the sum of all the areas. That's a right Riemann sum. Then take the limit as n goes to infinity, and consequently delta x goes to 0, and that gives us the definite integral. So the definite integral is an area. Wait a minute, the derivative is a slope, Definite integrals and area, how are those opposite to each other? Well, we see that it is kind of opposite of each other. So it may not seem like they are right away, but they are in fact somewhat opposite of each other. It's a remarkable result if you think of it that way. So the first part of the theorem says that the integral from a to x of f of t dt is a function of x whose derivative is the original function. Now a function with this property is called an antiderivative of the function f. So that the function, we'll call it a of x, because we're thinking of it as an area or a signed area, is the function a of x equals the integral from a to x of f of t dt. This is measuring the accumulation of signed area as x increases. So then its derivative, the derivative of the integral of f of t, is f of x, is the instantaneous rate of change in the area at a particular value of x. In other words, a prime of x is the rate at which the area is accumulating as we move to the right, and we found out that that is the same as the value of the function at the right end of that interval. So it's interesting, it's growing along essentially a line segment of length, the height of the function at that point. So that's kind of an interesting result there. Now one of the consequences of this that is really a cool consequence is this, that we can use this method to create new functions. Now we know how to make functions of various kinds. We've done this many times. We have some real basic functions, things like linear functions and exponential functions and polynomials and rational functions and power functions, and we might even go so far as to do things like logarithms and maybe even trig functions. But if we sort of call all those things elementary functions that we can build up out of combinations of addition, subtraction, multiplication, divisions, powers, roots, logarithms, and even throw in, say, maybe trig functions and their inverses, we've got a sort of a basic list of basic elementary functions. But it turns out there are functions, of course, lots and lots and lots of functions. Probably almost every function you've encountered in your life has been built up that way. But there are other functions, many of them in fact, that can be built up, that can't be built up out of those kind of functions, but yet they exist. And one way to get those functions is by using this method of integrating an existing function as part one of the theorem above. Now there are many of these functions, and you might think, well, okay, so what about these functions? Where do they come from? Where are they good for? Well, let me just give you one example. And it's a very, very important example. It's a normal probability distribution. And the normal probability distribution is a very, very important function in the study of probability and statistics. In fact, it's central to the study of probability and statistics. And it's extremely important, and probability and statistics are just everywhere. You pick up any newspaper, any magazine article, you pick up certainly research journals, and on any kind of field, you're going to see statistics all over the place. So statistics is a very, very important and very applicable area of mathematics that's going to kind of permeate all of society. So certainly this is very important. And the probability density function, the PDF for a standard normal distribution, is given by this formula. The PDF of x, or f of x, is 1 over the square root of 2 pi times e to the negative x squared over 2. That's a standard normal function, a normal function with mean 0 and standard deviation 1. The cumulative density function is a specific antiderivative of this function. And this particular antiderivative cannot be built up out of elementary functions. So there's no way to do the antiderivative without using some kind of some kind of integral. And so what this means is the CDF, which is the integral defined to be the integral from minus infinity to x of that PDF function, or it's because of the symmetry involved, it's also equivalent to 0.5 plus the integral from 0 to x of that PDF function. That turns out to be, especially this last version here, turns out to be a function of the kind that we have been talking about in part 1 of the theorem, the fundamental theorem. And so this is a function which we cannot write down with built up out of elementary functions. It's a function we cannot really write down the antiderivative in any other way. The PDF is a function whose antiderivative cannot be written down in any other way than basically what we've got it here, or something equivalent to that. So this is this CDF here for a normal distribution is an extremely important function in mathematics and in the world in general, and yet this is one that we need this first part of our theorem. And so this gives us a way of generating new functions, a new way of just expanding all kinds of functions. So it's a very powerful result there in and of itself. The part that we're going to spend more time on, particularly in our next unit or our next set of videos and notes, is going to be focused on really part 2 of the theorem. And one of the things that part 2 says, it says that if we're trying to find the definite integral of a derivative of a function, where in other words a rate of change of some function, then we can get that by finding the limit of Riemann sums. Of course, that's the actual definition of it, but the way we can find that and interpret it, it's a net change in the original function f, which is an antiderivative of the function we're given. Okay, so this often gives us an excellent interpretation of the definite integral. It makes it applicable to a wide variety of situations, and so by the way, this shouldn't seem so strange. Okay, because guess what? This is where we started. If we go all the way back to about 50 pages back to the very beginning of this set of notes and videos, we see that the first situation we looked at was a table of velocities and times. Well, what is velocity? Velocity is a derivative of position. So we were given the derivative of the position, and we were asking for the distance traveled, which was the net change in position. Okay, and so that's exactly what the second part of the theorem says. If we're going to integrate from a to b v of t dt, what we get is, of course, that's the integral from a to b of p prime of t dt, where p is the position, v is the velocity, t is time. What we ended up with is p of b minus p of a, the position at the end minus the position at the beginning, which is the change in p, which is the distance traveled. That's the whole thing we were trying to do at the very beginning that led us to the idea of the definite integral to start with. So in fact, this interpretation should not be a surprise to us when we think of it in that terms, because this is where we started at the beginning. So we have come full circle right back to where we started at the beginning of this playlist of videos and at the beginning of this set of notes about 50 pages ago. Now what the second part of this theorem allows us to do is to, especially the form I wrote it at the end, says if we can get our hands on an antiderivative of the integrand function, we can use that to find an exact value of the definite integral by finding the amount of change in this antiderivative, in other words, evaluating this antiderivative at both limits of the integral and subtract. So let's look at an example. We know that the derivative of 1/6 x to the 6th power is x to the 5th. We're using our power rule or power function rule there, shortcut rule from derivatives. So by the fundamental theorem of calculus, we see if we want to do the integral from 0 to 2 of x to the 5th dx, which by the way was the function, one of the functions we were trying to approximate earlier in the notes, and we looked at approximating it with several different methods. We see, according to the fundamental theorem, since that is integrating the derivative of 1/6 x to the 6th, that is 1/6 x to the 6th evaluated from 2 to 0. Now this notation is something new I've thrown in there, and that notation means what comes next. It means take that function, plug in the top number, minus take that function, plug in the bottom number for x. If it's clear that the variable is x, you could just put 0 and 2. If it's not so clear what you're substituting for, you might say x equals 0 and x equals 2 here. So in other words, according to the fundamental theorem, it is take the function we're taking the derivative of, an antiderivative of the original function, that is the 1/6 x to the 6th, and plug in the top number for x, and plug in the bottom number for x, and then subtract. Now 0 to the 6th is 0 times 1/6 is 0, so that term goes away. 2 to the 6th divided by 6 is 32/3, or 10.6 repeating. And if you remember back when we when he did this with Simpsons Rule, for example, somewhere back here, there it is, there's left Riemann sum with 4 intervals. It's the same function here. This is the area we're talking about right here that we're saying is 10.6 repeating. And we did it with the trapezoid, and there's the trapezoid rule with just 4 rectangles. And somewhere back here we did Simpsons Rule. Should be coming up pretty soon. There's midpoint estimate and then Simpsons Rule. And notice we did Simpsons Rule for this one with 4 rectangles, and we got pretty good. Here it is. There it was. 10.671875 is what Simpsons Rule came up with. The actual answer, as we've just seen, is 10.6 with the 6 repeating. Of course, if we had used a larger n, our Simpsons Rule, or any of them, left, right, trapezoid, midpoint rule, all of them would have been much better estimates. So anyway, that's how you can do a definite integral. So basically we want to find a definite integral. To do it exactly, we will never do it by the definition. What we will do is either use the fundamental theorem, just like we did in this example, by getting our hands on an antiderivative, evaluating the 2 endpoints and subtracting, and we'll have to do it that way for an exact value. Or if we don't want an exact value, we just want a decimal approximation, we could do it this way and then approximate the final answer like we have here, rounded off to a certain number of places. Or we could just use Simpsons Rule, or equivalently the integration capabilities of our calculator. Sometimes, however, though, as we've seen up above with the normal distribution function, we may come across a function for which there is no antiderivative built up out of elementary functions. And so if you want a numerical answer for an output there, the only choice you have is to use something like Simpsons Rule, an approximation technique. So again, one should remember that the definite integral is actually a limit of Riemann sums, and that using the fundamental theorem to calculate the value of the definite integral is really a shortcut, similar to using the derivative shortcut rules to compute derivatives, which is actually a limit of difference quotients. However, in practice, one never does that directly. One uses this, and somehow you can also see that this gives us some further interpretations of the definite integral, which we'll see. So finally, conclusion for this playlist: not only does the first part of the Fundamental Theorem of Calculus tell us that derivatives and indefinite integrals are in a sense inverses of each other, it also gives us a way to create new functions which are not built up out of elementary functions. And not only does the second part of the theorem continue to reinforce this view of derivatives and integrals as inverses, but it also gives us a way to calculate the exact value of a definite integral of any function for which we can find the formula for an antiderivative. In our next set of videos, in our next playlist, we'll use this technique to we'll begin to focus on how do we find these formulas for antiderivatives, this process of anti-differentiation or integration, and we'll use that to find exact values of several definite integrals. So, in conclusion, the fundamental theorem is a very, very powerful result. It is really one of the things that makes calculus work, and it connects the 2 main branches of calculus: integral calculus and differential calculus.